Hello class. Today we are going to start talking about right triangles, and we're going to get into a little bit of trigonometry eventually in this chapter, but we're going to start with the Pythagorean theorem. All right. Pretty much the basis of all of the right triangles information that we're going to do over the next couple of videos is going to start with Pythagorean theorem. And this hopefully is going to start off as a review. Pretty much everybody remembers the Pythagorean theorem, right? A squared plus b squared equals c squared. And so what we have here, the way this works, if you have a right triangle, the sum of the lengths, the sum of the squares of the legs is going to add up to the square of the hypotenuse. All right. So the length of a squared plus the length of b squared is going to equal the length of c squared. All right, and this is Pythagorean theorem, and y'all all remember this. You've been dealing with this for quite a while, probably. We do have some Pythagorean triples, and what a Pythagorean triple is, these are just a triangle where the lengths of all the sides are integers, all right, which most right triangles do not have integers for all of their sides. You might have it for 2, but not for 3. So the ones that do are special. We call them Pythagorean triples. And here are just a few of them. The most common ones are 3, 4, 5, which is the easiest one to remember. I love that one because it's 3, 4, 5. There it is. Because 3 squared plus 4 squared equals 5 squared. 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. All right. Remember, very important, C, the hypotenuse is always that longest side. But what's cool about these are all Pythagorean triples, which means if you double the sides, or you triple the sides, or you quadruple the sides, it's still going to work. So 3, 4, 5 works, 6, 8, 10 works, and so does 9, 12, and 15. Because if you're just tripling all the sides or doubling all the sides, you're multiplying it by some scale factor, it's going to be similar, right? And so if this one works, doubling everything, it's a similar triangle, everything's proportional, the angles are all the same. And so it's still going to work. The side lengths are just multiplied by some scale factor. So it's all good. All right. So we're going to use those. We like those. They make things easy for us. So it's good to have those memorized, because then when you have, like, for example, if you see some right triangle and you're solving for the missing side, and you see 2 of the sides are 3 and 4, you don't even have to work it out. You can know automatically, hey, that's going to be 5. It's 3, 4, 5. All right. And so having at least these first couple memorized, especially this one, that's the one you see all the time. But if you have these 2 here memorized, or these top row memorized, it makes it very easy to solve a lot of mathematical problems. All right. All right. 9.2, the converse of the Pythagorean theorem. What this says is if a squared plus b squared really does equal c squared, then your triangle is going to be a right triangle. All right. So the Pythagorean theorem says if you know that it's a right triangle, then you can conclude that a squared plus b squared is going to equal the length of the hypotenuse squared. What the converse says is if you know that the hypotenuse squared is equal to the legs squared, then it's going to be a right triangle, because that's the only kind of triangle that the Pythagorean theorem works for. If it's not a right triangle, Pythagorean theorem is not going to work. Which brings up the question, what if it doesn't work? What if c squared is less than a squared and b squared? Well, what if it's more than a squared and b squared? And this is the Pythagorean theorem, the Pythagorean inequalities theorem. All right. What this says is if c squared is less than a squared plus b squared, you're going to have an acute triangle. If c squared is more than a squared plus b squared, then you're going to have an obtuse triangle. All right. And the easy way to remember this, if it's less than a squared and b squared, that means it didn't reach, right? You had your a, you had your b, you had your legs there, and the long side wasn't long enough to push this side AB, there's AC, out to a right angle. It wasn't long enough, so it had to bend in, and the angle had to cave in a little bit in order to make these reach, right? So you have an acute triangle. Over here, C was too long. You know, you wanted it to just go to right here, but it was too long, and so you're sticking out over here. And so our triangle, the angle is too big, and so we have an obtuse triangle. All right? And so this is the Pythagorean inequalities theorem, which is still pretty easy stuff. Okay, so let's open this up. Let's do a couple of examples. See what we got. A lot of this is going to be simple stuff you've done for years, and so it's not going to be a big deal because we've done this for a long time. Okay, so exercise 1 through 6, we need to find the value of x. Tell whether the side lengths form a Pythagorean triple. Okay, so again, we saw that it is a Pythagorean triple if all of the side lengths are integers. So if x comes out to an integer, then we're going to have a Pythagorean triple. So let's see what we have. We know that they are all right triangles. So x here, it's the side opposite the right angle, which means this is going to be the hypotenuse, this is the c, right? So what we have a squared, 81 squared, plus 108 squared, which is going to equal x squared. So what we're going to do, we just want x. So the square root of, and I am going to use my calculator because I cannot do all of these in my head. So here we go. 81 squared plus 108 squared is 18,225. So I have 18,225 equals x for the square root of that. So let's get the square root here. So here we go, and we want to second square root, and then second answer, and we have everybody's favorite pair of shoes, and we get 135. So that came out nice and neat. 135 equals x. So is this a Pythagorean triple? Well, that's an integer, that's an integer, that's an integer. They're all nice whole numbers, and so yes, this is a triple. This is a triple. Let's try the next one. Number 2, we have 8, 4, and x. Now on this one, 8 is my long side, right? 8 is my c. So what I have here is x squared plus 4 squared equals 8 squared. I'm solving for x, so of course we're going to subtract the 4 squared over there. And we're going to end up with x equals the square root of 8 squared minus 4 squared, which is, let's see here, 8 squared minus 4 squared. We get 48. So we have the square root of 48. 48 is not a perfect square. Not going to work. 49 is. That would be 7, but this is not. So it's no good. So we know since that is not a perfect square, we don't have an integer here. This is going to not be a triple. So I'm going to write that over here. Not a triple. But I need to know what this is. And I don't want to leave it as a decimal because it's going to be ugly, right? It's going to be irrational. It's going to go on forever. So what we're going to do is we are going to simplify this radical. Hopefully you remember how to do it. If not, we're just going to do it real quickly. So that's okay. We will remind you. So what we're going to do, we're going to do this prime factorization stuff that hopefully you remember to do, the little factor trees, right? So 48 is divisible by lots of different things. We'll go with 4, right? So divisible by 4. And what we're looking for are perfect squares or pairs of factors, right? And let's see here. So 4 times 12 is 48. 4 is a perfect square. So we have the square root of 4, well, the square root of 4 is 2. 12 is not a perfect square, so we need to factor that again. So we have the square root of 4 and the square root of 3. Okay, so 4, once again, that is a perfect square, so that is 2. And square root of 3 is 3, and we can't do that. And we have 3, which is prime, so we can't factor that anymore. So we're left with square root of 3 times 2 times 2. Well, so x equals 2 times 2, which is 4 times the square root of 3. So 4 square roots of 3. Not a triple, because that is not a whole number. That's a hideous decimal, so it's no good. Okay, let's take a look at number 3. Number 3, once again, x is across from that right angle, so this is my hypotenuse. This is going to be c in the Pythagorean theorem. Let's change the color so these don't blend together. All right, so what we have is 20 squared plus 15 squared is going to equal x squared, because this is my big side. So we have the square root of whatever that is. I do not remember what that is. Let's find out. 20 squared plus 15 squared is, that's not too bad, 625. 625 is going to equal x. Is this a perfect square? Well, let's find out. Second square root, second answer, and that is 25. So x equals 25. Is this a Pythagorean triple? Because that was the question, right? Is this a whole number? Is this a whole number? Is this a whole number? The answer to all of those is yes. So the answer to is it a triple is also yes. This is a triple. T-R-I-P, helps if I could spell, L-E. And in fact, if we'll look back here, we will see somewhere over here. I'm pretty sure it was on there. Is it? I guess not. 1525, yeah. What that would be is if I took all of these and multiplied these by 5, right? 3 times 5 is 15, 4 times 5 is 20, and 5 times 5 is 25. So there it is. So it's in this one. It would be down this table if you extended this out farther. Right? There it is. All right, let's take a look at number 4. Okay, x, once again, is across from the hypotenuse. So once again, we are looking at x being the c position. All right, so we have 6 squared plus 10 squared equals x squared. Let's see here. So we're going to have the square root of something. What is that, 136? Right? 6 squared plus 10 squared, yeah, that'd be 36 plus 100, 136. All right, 136 equals x. The square root of 136, yeah, it's going to be some great big nasty irrational decimal, right? Yeah. So it's not a whole number, so this is not a triple. Not a triple. But again, we don't want to leave it like that. We have to simplify our answer. And we don't want to put some hideous decimal because that has to be rounded and it's not precise. So let's simplify it. Do our little factor tree. So we're going to have the square root of something and the square root of something. Okay, let's see it. Well, 36. Not sure. It is divisible by 2. I can go that far. I know it's even, so it's divisible by 2. So let's see here. 2 times what? 136 divided by 2 is 68. All right. 68. Neither one of those are perfect squares, so we're going to do this again. Let's see here. Fact 2 is prime, so that's done. Square root of, what do we got? Divisible by 2 again. All right, because it's even. So that would be 34. Okay, 2 is prime, so that's done. 34, well, it's divisible by 2 again, so let's do another 2. So 2 and 17. Well, those are both prime, so that means we're done. So we end up with square root of 2, square root of 2, square root of 2, and the square root of 17. And remember, when we did this before, we were looking for pairs and perfect squares. Well, we didn't find any perfect squares, but we do have a pair of 2's. And the square root of 2 times the square root of 2 is 2. So we have these 2 that are going to come together as just 2 outside of the square root. And then we have these 2 left over. So we have x equals 2 times the square root of 2 times 17, which is right back here at 34. So it is not a triple because x is 2 times the square root of 34. which is not a whole number. It's irrational. It goes on forever, and it's hideous. All right, we do have two more of these, and I would like for you to work these two out on your own. So do 5 and 6, see what you get for x, and then determine, is it going to be a Pythagorean triple? Then come back and check your work. All right, let's see how you did. On number 5, x is not the long side, so x is not the hypotenuse, because the hypotenuse is the 77 across from the square root there, so it's not going to be c. What we're going to have here is 77 squared equals 55 squared plus x squared. Subtract that 55 over, and we end up with the square root of 77 squared minus 55 squared is going to equal x. I have no idea what that is. Something big. So let's see here. 77 squared. That's not a square. Clear. 77 squared minus 55 squared is 2,904. So we have the square root of 2,904, which I do not believe is a perfect square. Let's test it. Nope. So, not a perfect square. Got all the irrational decimals at the end there, so this is not going to be a triple. Not a triple. Let's find out what it is. Now this is a big one, so we're probably going to have a great big tree here, right? Okay, and that is a 4. Okay. So, well, the last two digits are divisible by 4. 0, 4 is divisible by 4, and so I know that this is going to be divisible by 4. I don't know what the rest of it is, but I do know it's divisible by 4. So let's see here. We had 2,904 divided by 4 gives us 726. All right, 726. Let's see here. It ends in a 6. We might have to try 3. So 7 plus 2 is 9, plus 6 is 15. 15 is divisible by 3, which means that this is divisible by 3. It's not divisible by 9, though, because then they would all add up to a 9, and they don't. So I can divide out a 3. Let's divide a 3 out. Because 26 isn't divisible by 4. That would be bigger and that would be better, but it's not. So we'll divide it by 3. So divide by 3, 242. 242. And interesting thing, since this is a palindrome, that it is probably divisible by 11. Notice it's the same forward and backwards. If you have a 3-digit number that's the same forward and backwards, it's probably divisible by 11. Not always, but a lot of the times. So let's try that. Make sure before I write it. Ah, it is good. Divided by 11 is 22. Okay. So let's do square root of 11, square root of 22. 22 I can do. That is the square root of 11 times the square root of 2. Okay, so we said that we were looking for pairs and we were looking for squares. That's an 11. That looks like a, I don't know, looks like an N. That's an 11. As is this, not a 4, 11. Well, I do have a perfect square here. Square root of 4 is 2, so that can come out. And I do have a pair of 11s. Right there, I got a pair of 11s. Right, so that's done. A pair of 11s are going to come out here. That's just going to be 11. And then I have a square root of 3 that I can't pair up, and a square root of 2 that I can't pair up. So we end up with x equals 2 times 11, which is 22, times the square root of 3 times 2, which is 6. So x is 22 times the square root of 6. There it is. Not very pleasant, which is why it's not a triple. So it's no good. Okay, let's try number 6. Hopefully you got this one right as well. So x we see is the hypotenuse. So this is in the C position, which makes it nice. So we have 48 squared plus 90 squared equals x squared. So we're going to end up with x equals the square root of, let's find out here, 48 squared plus plus 90 squared equals about 10,404. And that's interesting. Let's see, is it a square root? Second squared, second answer. No, not question. Second answer. There we go. 102. So 102 equals x. This is a whole number, which means this is going to be a triple. That is a p triple. I don't know why I can't write p's. I don't know. Triple. My fingers are not working today. Alright, this is a triple. Alright, so there's that. Hopefully you got those right. Not too bad. Let's take a look at number 7. From school, you biked 1.2 miles due south, then half a mile due east to your house. If you had biked home on a street that runs directly diagonal from your school to your house, how many fewer miles would you have biked? Alright, this sounds like a time to draw a picture. So let's see, we were at school right here. We went due south, so straight down 1.2 miles. Then we turned due east, which would be this way, for 0.5 miles, 0.5. And we arrived right here at home. And the question is, if we had gone down some other street that went straight from school to home, how many fewer miles would we have gone? Now, since we were going due south and then due east, that means we turned 90 degrees, right? Which means this is a right triangle. So we can figure out how many miles that is by plugging into the Pythagorean theorem. So, let's see, this one, the one that we are looking for, is across from the right angle. So this is our hypotenuse. This is going to be C. So we have 1.2 squared plus 0.5 squared equals C squared. So that means we have the square root of, whatever that is, let's see here, 1.2 squared plus 0.5 squared, which is 1.69. So there we go, 1.69. And hopefully that will come out nice and neat. Always fun when you're square rooting decimals. So square root of my answer, 1.3. That's not bad. Alright. So 1.3 equals C. So this is 1.3 miles right there. But that wasn't the question. The question wasn't how far would that have been. The question is how many fewer miles would you have biked? So how many miles would this have shaved off your biking distance? So how many miles did you bike? Well, what you biked was 1.2 plus 0.5, so that is 1.7. That's how many you did bike, minus what you could have done, minus 1.3, and you end up with, you could have biked 0.4 miles fewer. So 0.4 fewer miles is what it would have saved you. Alright, let's take a look at 8, 9, and 10. I don't know why it says just 8 and 9. Anyways, so for 8, 9, and 10, verify that the segment lengths form a triangle. Then, is the triangle acute, right, or obtuse? Okay, so first we have to verify that these really are going to be a triangle, because if it's not a triangle, then it's not acute, right, or obtuse. And if you remember, the triangle inequality theorem says that for any triangle, the two smaller sides will add up to be more than the longer side. So the smaller sides here are 6 and 5. So 6 plus 5 has to be greater than the other long side, which is 7. And that works out. So yes, it is a triangle. Let's find out which one. And for that, remember, we're going to use the Pythagorean inequalities theorem. So we take these two and we kind of just square everything. So we have 6 squared plus 5 squared, and it's going to be something in regards to 7 squared. Might be equal, might be less than, might be more than. We don't know. So let's see here. We have 6 squared plus 5 squared, which equals 61. So 61 and 7 squared, we don't need a calculator for that, that's 49. And so 49 is less than that. So the C, the long side, was less than the other two. The C squared was less than A squared plus B squared, which means, if we see over here, that C squared wasn't long enough, was it? It's not long enough to make it a right angle, and so it's too short. This is acute. Acute. All right. I would like for you to pause the video now and work out number 9 and number 10. All right, let's see how you did. So first we need to verify that this works, and we almost don't even have to do anything because 90 plus 216 is obviously going to be more than 234, right? That is my big one. So it's going to be 3 something. Who cares? Anyways, it's more than that. That's all that really matters. We have 90 squared plus 216 squared is, I don't know, maybe going to equal something to 234 squared. All right, so let's see what we get here. Tell the phone to shut up. And we had 90 squared plus 216 squared, which is a great big number, 54,756. And let's check the other one, 234 squared, which is 54,756. Hey, it does equal. Oh, it does equal. All right. 54,756. So that does, it equals, it checks out. So what is this? Well, it works. A squared plus B squared equals C squared. So this must be a right triangle. This is a right triangle. All right, last one. Let's see. Does 1 plus 1, is that more than the square root of 3? Well, for that, you kind of got to know what the square root of 3 is, don't you? Well, let's find out. Square root of 3 is 1.7. And 1 plus 1 is 2, which is more than 1.7, so this is going to be a triangle. So just to verify, 1 plus 1 is greater than the square root of 3, so that checks out. Okay. Now, we're just going to take this, plug this into Pythagorean Theorem. That is our big side. So 1 squared plus 1 squared is, I don't know, maybe equal to the square root of 3 squared. Well, let's see. So 1 squared plus 1 squared, that's going to be 2. And the square root of 3 squared, well, when you square a square root, they cancel out, right? You end up with 3. And so here we have that C squared is longer than A squared plus B squared, which means it's too big. It's not going to fit. And so we can't make it a right triangle because our C is too big and it's going to push the side out over to the side, and this is going to be obtuse. All right. And there it is. So not too bad. Not too bad at all. So here we have a nice little review of the Pythagorean Theorem. All right. Some Pythagorean triples. Good stuff to write down. Make sure you have that. It will help you out on a lot of stuff. All right. And then we expanded on that one a little farther than you probably went in junior high or something. And we talked about what happens if C squared is more than A squared plus B squared. What if it's less than A squared and plus B squared? Remember, if C squared is less than A squared plus B squared, you have an acute triangle because C is too short. If C squared is more than A squared plus B squared, then you have an obtuse triangle because it's too long. And if it exactly equals, then you have a right triangle. And I hope you found that useful. And I'll see you in the next video.